Hello and welcome to the second part of this week's learning in Nature's Chemistry. We're looking at the chemistry of cooking in this section, and we're looking at something called the oxidation of food and antioxidants. So antioxidants are something you may have heard of already. Oxidation of food ties into the previous stuff we did on oxidation when we looked at oxidation of alcohols to produce aldehydes and ketones. So if you're looking at Scholar or BBC Bite Size or the SQA specification, all of this stuff, aldehydes, ketones, and all of that comes under the title Oxidation of Food, but I've broken it up into two different sections. So let's get started. Our learning intentions for this section, and we should be able to describe how food is oxidized and the effect of oxidation on flavour or aroma molecules, which are aldehydes. You might be able to guess that already. You should be able to describe the effect of oxidation on edible oils and fats. So that's a key new bit for this section. Nice and simple though, really. You should be able to explain how to prevent the oxidation of food, and you should be able to identify antioxidants from redox equations as they are the substance being oxidized. I've kind of given the game away, but we're going to look at how that's done. And we're going to actually start with this little bit about how we can identify the substance being oxidized in redox equations, and then we'll look at antioxidants later on. So my starter question is to do with how we can identify substances being oxidized, and I want you to give two examples of how you might recognise an oxidation reaction from the chemical equation. So if you're given a chemical equation, I've just written X changes into Y, and what things might tell you that that is oxidation. If you have space, you could write the answers down, but you don't necessarily need to for this. Okay, so make sure you pause the video if you want to write them down. Okay. So what I've said here, two different ways we can recognise oxidation. First of all, we can think of oil rig. Oxidation is the loss of electrons, so if there were electrons on the product side, that would indicate that this was an oxidation reaction. Second thing is oxidation. The definition we learned in the previous topic is an increase in the O to H ratio, i.e. what that means is more oxygen or less hydrogen. So that's your two ways, and just a little example of this is methanol has a 1:4 oxygen to hydrogen ratio, and if it's changed into methanal, the aldehyde, it changes into a 1:2 O to H ratio, so we've got less hydrogen per oxygen, or an increase in the O to H ratio. Okay, so oxidation of food. Oxidation reactions can occur when food is exposed to oxygen in the air, so it's as simple as that. That's what you need to remember about how food is oxidized. It happens when it's exposed to oxygen in the air. So one of the kind of most common things you might recognise or remember is if you chop apples, then the apples can quite quickly turn brown, so that's an example of oxidation. It is actually catalysed by enzymes, but still oxidation. Food can also just decompose, and I would say that there's a difference between just general decomposition and oxidation, but you don't need to get into the details of that. So lots of foods can undergo oxidation. In terms of the food industry, foods containing fats or oils are at the greatest risk of oxidation, and that's why this topic is kind of being put in here, because it's quite important in the food industry. So when we oxidize fats, what happens is oxygen from the air, first of all, can react, and it tends to happen at a double bond position in the fatty acid chain. So here's our information here. So oxygen can react with fats and oils in food, and the fatty acid chains break at the carbon-to-carbon double bond positions. What this means is that foods containing highly unsaturated fats and oils, ones with a lot of double bonds, are more susceptible to oxidation. So the other thing that can happen with oxidation is that as well as breaking down the fatty acid chain, this releases then other molecules like free fatty acids, aldehydes. It's actually a really, really complex process, and you don't need to know the details of how that happens, but you do need to know that some of the products of oxidation of fats are volatile molecules which give foods an unpleasant smell. And the key thing to remember, this comes up a lot in exams and multiple choice questions, etc., is when a fat or oil is oxidized in this way, it is often described as having turned rancid. So you often you see that word coming up. What is the word used to describe fats or oils that have been oxidized? and we say they turn rancid. And like I mentioned, oils with a high number of double bonds are particularly susceptible to oxidation. So the picture here is showing a nice piece, I think it's a sardine. Oily fish it's very good for you. It has a lot of unsaturated fats, but it smells really bad when it goes off because these unsaturated fats turn rancid. So that might give you a little hint for question 1 of the notes. Okay, so as well as fats and oils, it's also worth remembering that other things can oxidize as well. Aldehydes will oxidize to produce carboxylic acids, and this completely alters the flavour of the food. Another good example is that oxidation of ethanol in alcoholic drinks will first oxidize to the aldehyde ethanal and then quite quickly to ethanoic acid, which is just vinegar. So again, this totally alters the flavour and also the appearance of the drink. So for question 2, we're talking about the oxidation of ethanol to ethanal and then to ethanoic acid, and I'm asking you to explain why the equation shows it's an oxidation sequence. So all you have to do is work out the O to H ratio for this for each different compound, and remember that oxidation is an increase in the O to H ratio, so you just need to write a wee sentence to explain that fact. So this slide is just a little summary of the effects of oxidation on food which we've discussed. So we can get a deterioration of flavour and a bad smell, and with fats and oils that's called rancidity. We can also get a loss of colour and a loss of nutritional value. So just again to highlight the importance of this, foods containing fats and oils are most likely to have problems with oxidation. So a lot of kind of quite commercially produced foods like donuts, cakes, all that kind of stuff, and we're going to need to find some way of protecting them from oxidation, as well as protecting them kind of in the supermarket, for example. Protecting fats and oils from oxidation is a major issue in the manufacturing stage of many of these foods. For example, when butter or margarine is stored and used in a biscuit factory, that's quite susceptible to oxidation, and you can imagine if you're making an enormous quantity of biscuits in a factory, it would be a real disaster. You'd lose a lot of money if your fat or oil or whatever you're using became oxidized. So that's one of the main reasons why oxidation of food is a big issue and why we have to prevent it. So we're going to look now at a couple of different ways in which we can prevent the oxidation of foods. So the first and simplest one is packaging. So this is question 3 of the notes, and I want you to think about how packaging can help to prevent oxidation of foods. It's just what comes into your head first is probably right. So pause the video now if you want and try and write a couple of things down, and then I'll move on to the next slide. Okay, so we've got some examples of packaged food here. Basically, sealed packaging, the main thing it does is it minimises the availability of oxygen because it seals the foodstuff off from the air. So crisp packets are a good example of that. Some things are even vacuum packed. So mackerel is an oily fish. We mentioned that they are very susceptible to oxidation, but when you buy these, they're often vacuum packed, so it just completely removes oxygen. Some other foods as well, like salads, and I think crisps maybe as well, are packaged in an inert atmosphere of nitrogen only, so that's another kind of chemical solution, but more to do with packaging. So we just remove oxygen completely. Okay, so the packaging side, it works really well for products that you're buying in the shop, but we mentioned that oxidation can be a major problem in manufacturing, and also there are some things that just don't package that well. I don't think I would like a piece of vacuum packed cake very much. So there's also a kind of chemical solution to preventing oxidation, and we use something known as antioxidants. So that's quite nice and easy to remember. Antioxidants prevent oxidation. So these can be added to food, and they are compounds that oxidize in preference to the food. So this is where it gets perhaps a little bit confusing. So you may have heard of antioxidants. Antioxidants are generally considered to be very good for us, and we might talk about that a little bit more when we look at the skincare section. So antioxidants prevent oxidation, but they oxidize in preference to to the food. So you could say that the antioxidant is preferentially oxidized and sacrificed to protect the food compounds. So the thing to remember is that antioxidants prevent oxidation by being oxidized themselves, and that's how you can recognize an antioxidant. So we'll look at a couple of examples now. Vitamin C is a really common antioxidant. You don't often see vitamin C on the label of food packaging, but you very frequently will see ascorbic acid. So if you look at a packet of food that you've got in the kitchen, you probably, chances are you might see ascorbic acid on the label if it's got quite a few ingredients. So vitamin C is a water-soluble compound, and it's one of the most common antioxidants that's added to food. So we're going to take a little look at the equation for oxidation of vitamin C. So the antioxidant vitamin C can act as a reducing agent, so it's an electron donor. It prevents oxidation of the foodstuff by itself being oxidized. So to be honest, I think this little sentence here, you've got that in your notes as well, but it's quite confusing. You could even just cross it out. The most important thing is to remember that antioxidants are oxidized themselves. Okay, so here's the ion electron equation I've asked you to complete. This is just going to be done in exactly the same way as any other ion electron equation. So first we have to balance elements that are not hydrogen and oxygen, or at least just check that they are balanced. And then we balance oxygen, and if oxygen is unbalanced, we would add water. And then we would balance hydrogen, and if hydrogen is unbalanced, we would add H+ ions. And then finally, to balance the charge, we'll add electrons. So pause the video now and give this a go yourselves. Okay, moving on. So I didn't mention actually, vitamin C, ascorbic acid, when it's oxidized, we can also call it dihydroascorbic acid. Dihydro, just because we've removed 2 hydrogens here. Okay, so this is the structure of vitamin C. This has come up a couple times already, and you don't need to know the details of how those hydrogen atoms are removed. It's just down here where they are removed, these hydrogens here. So that's your completed oxidation equation. You've got your 2H+ to balance the hydrogens, and then your 2E- to balance the charge, because this side is neutral. So we've got our 2 positive charges and our 2 negative charges on this side, which cancel out to make both sides neutral. So our charges have to balance on both sides. Okay, so now I'd like you to have a go at completing question 5 and 6 of the notes. You should be able to do this based on the information that we discussed in the starter question. So pause the video now and complete this before moving on to the answers. Okay, so here's my O to H ratios, and then for question 6, there's a couple different things you can say, but importantly, you need to say that antioxidants are oxidized themselves, and that's how you recognize them in preference to the food. And you need to then mention how the equation shows that vitamin C is oxidized. So you can either mention that it loses electrons, or you could say that O to H ratio increases. Either of those would be fine for that question. Okay, so just another example of an everyday use of this. We discussed apples browning. If you dip the apple in, I know the picture shows orange juice, but probably the more likely one to use would be lemon juice, and that contains vitamin C, which will prevent the apple from going brown. So if you're making like a fruit salad or something and you're chopping your apples, top tip is to squeeze, or even a crumble, just squeeze some lemon juice over it if you want to stop it from getting oxidized, turning brown before you have time to cook it or eat it. Okay, or orange juice, actually, that would be nicer in a fruit salad than lemon juice. Okay, moving on. So vitamin C is a natural antioxidant, but we can also use synthetic antioxidants, BHA and BHT, and then we've got vitamin E, which is another antioxidant. These ones on this slide, BHA, BHT and vitamin E, are used to prevent oxidation of edible fats and oils. So BHA is called butylated hydroanisole. I think there's an X missing in there actually. I think it should be butylated hydroxyanisole. and this one is butylated toluene. So we're going to look at the structures in a minute, but the main reason these other ones are used rather than vitamin C is that they are soluble in fats and oils. So that might give you a clue for question 7. So the structures are given just here. We're using the skeletal formula for these because they're quite complex molecules. You absolutely do not need to learn these structures, okay? You don't even really need to learn these names, but it's probably worth learning one as an example. Okay, so you can see that these are more likely to be soluble in fats and oils because although there is maybe one hydroxyl group per molecule, the vast majority of these large molecules are just hydrocarbon only sections. So overall the molecule is mostly non-polar and therefore more soluble in fats and oils. Okay, so those antioxidants that I mentioned on the previous slide, you can recognise them in food. They probably won't be listed on the ingredients list as butylated hydroxyanisole, but they are given different E numbers. So some of the E numbers that you might see on packaged foods relate to these antioxidants. Okay, so that's been hopefully a reasonably quick overview of antioxidants. But I hope that we've covered everything. So you should be able to describe how food is oxidized and the effects of oxidation on flavour or aroma molecules, which are aldehydes. You should be able to describe the effect of oxidation on edible oils and fats. So this top one, how is food oxidized? All we're looking for is it's oxidized by reaction with oxygen in the air. That's all I'm thinking with this one. And aldehydes, the flavour's changed. That's the main one you need to know. Can you remember how we describe the effect of oxidation on oils and fats? That is an important key word. It means they smell really bad. What do you think it is? It's rancid. Okay, so that's the key word for this one. We can describe oxidation of fats and oils as them turning rancid. Okay, how do we prevent the oxidation of foods? 2 different ways. Hopefully you're thinking of packaging and antioxidants. And how can we identify antioxidants from redox equations? Well, it's given I've given it in the sentence, unfortunately. So it's the substance being oxidized that is an antioxidant in the context of food and oxidation of carbon-based compounds. Okay, thank you very much for listening, and I hope you get on okay with this section.